etc., and plants. But we're not going to be, so plants, algae, etc. And also, bacteria. Aerobic bacteria will use up oxygen. So there are other factors, but we're mostly concentrating with this instrumentation course on the three factors: the temperature, atmospheric pressure, and impurities in the water. So the amount of oxygen that a given volume of water can hold is a function of atmospheric pressure. Higher the atmospheric pressure, the more oxygen that is pushed into the water. Temperature of the water, you get more oxygen at lower temperatures. And the more substances, the more salts or dissolved substance in the water, then the less oxygen that room for the oxygen molecules to be in the water. Oh, by the way, this is important. This obviously will show up on this exam. I mean, okay, if I was a betting person, I bet this would be on the coming quizzes and exams. So know this slide, star it, read it, memorize it. Every night before you go to bed, I want everybody to kneel down and recite this, as well as everything else about instrumentation, and then you can go to bed. And this is a terrible slide, but you may actually see this on an exam. The reason it's terrible is you can barely see these arrows. But basically, as water temperature increases, DO decreases. Salinity increases, DO decreases, and as atmospheric pressure increases, DO increases. Good. In the olden days, I did refer to these tables that were needed to calibrate instruments. If you are working in a plant that have galvanic or potentiometric sensors, you will have to use this table. It's very simple to use. This one happens to be in feet, mainly because most of our instruments are now LDO instruments. They don't need this table, so nobody's bothered converting this into metric. I'm sure there are some tables out there like that. And so you just cross-reference elevation and degrees centigrade, and you may want to ideally calibrate this instrument on a day where atmospheric pressure is normal, and normal being about 760 millimeters of mercury. And that you can get from weather, from the internet or weather channels or whatever. All right, that's enough with DO. I'll leave it up to Dave and biology and chem to teach the rest. But for the instruments, there are basically three methods that are widely used to measure DO. First one is laboratory methods, for instance, Winkler method. Second one are membrane dissolved oxygen probes. So I mentioned them before, and we'll get into greater detail with them in a bit. And the third one is optical dissolved oxygen probes. They're usually just called LDOs, luminescent dissolved oxygen probe. So LDOs. Oh, bloody heck. How the heck do I check my... Somebody has to tell me how to check my chat messages. Oh, I'll try that. Oh, no. All right. Whatever. Please raise your hand if, this is a bit of a learning thing for me. I was using Harjeet earlier as my guinea pig, so that's the only one I see. No, wait. Okay. So into your saltiness. Thank you. All right, good. Yeah, Frank's trying to learn this, and so please bear with me. And just testing my mic. Good. Okay, good. All right, so we're not going to be discussing laboratory methods here. We will be discussing 2 and 3. So membrane dissolved oxygens. Frank is going to fast forward just a few slides. I will be returning to this slide 16, in a second. But I'm going to show you this slide here. Basically, what a membrane is, well, okay, everybody knows what a membrane is. But these membranes have a size that only allow oxygen molecules to pass. So water molecules will not, they're too large to pass through. So yeah, so the oxygen molecule will be able to permeate this membrane. So the membrane dissolved oxygen uses this permeable membrane to allow the oxygen to pass through. And there's an electrochemical process involving an anode and cathode that react with the oxygen molecules and produce either a voltage or reduces the anode cathodes and takes a voltage. So I mentioned the permeable membrane, and it's quite easy. When unfortunately, those who have not done the lab will have to see them next semester. But you can actually see the membrane on these, as opposed to an LDO, which just has a flashing light. There are 2 fundamental techniques for the membrane DO sensors. The first is a galvanic DO probe, and the second one is a polarographic or a potentiometric. Yeah, usually called, well, both. Polarographic, just for our course, is good enough. Both have an anode and cathode, and both are basically obsolete now. The polarographic came out, I believe, darn, I used to know the date, early 1900s. So it's been around for a very long time. The galvanic probe came out in, I believe, 1964. So it would be 56 years old now. They both had their advantages and disadvantages. You are required to know the advantages and disadvantages of both, as well as how to maintain them. So yeah, I'll have a video. I'll post a video later on how to maintain them, the membrane type sensors. Oh, who's my timekeeper? Can my timekeeper please put up their hand? And also, Kelsey, you are. Thanks, Aaron. Okay, all right. My apologies, Ron. Can you please turn off your mic and yell at me when it's time to take a break? So let's stop at 9:50. I know everybody can just sort of go and hopefully still see, especially if you're on a Bluetooth mic or earphones. But yeah, please let's stop for a break at 9:50. So Aaron, if you can, yell at me then. Otherwise, I won't notice. Okay. Anyways, the main distinction between the polarographic and the galvanic probe is the polarographic needs an external voltage applied to it, whereas the galvanic, based on the solution and the amount of oxygen molecules in that solution that manage to go through the permeable membrane, will create a voltage. So I mentioned before that the polarographic or potentiometric is older, and up until 10 years ago, we were probably the only place in BC that still actually used this kind of setting. 1 second, I'm hoping. Okay, good, thanks. Yes, however, you may actually end up seeing it out there in the real world. So you have to know it. The galvanic sensors, again, we were using it right up until very recently, especially in C-158, just before Dave came. And you will probably find them out in the field. However, most are being replaced with the LDO, the luminescent dissolved oxygen. So this is a breakdown of the galvanic probe. Basically, you would unscrew this, and inside this probe is a caustic solution that will interact with the anode and cathode. So I'm going by memory. I do believe that the anode is gold, or cathode is gold, the anode is lead for galvanic, but potentiometric or polarographic, it's platinum and silver, I think. Yeah, you don't need to know the types of metals used. Just know that the galvanic probe acts like a battery. So because of the caustic solution and with the introduction of oxygen molecules, the anode is reduced, and the cathode, there's a reduction taking place, and that produces a voltage based on the amount of oxygen molecules inside the probe. So maintenance, there's not much to do. Well, actually, for a galvanic probe, you do have to maintain them fairly regularly, about a month, once a month. Same with calibration, maybe once a week to once a month, because the solution does get used up. The anode and cathode, well, the anode can be used up. So you can see right here a little nut to take off the anode and replace it. And yeah, the solution, like I said, has to be refilled every once in a while, new solution put in. And sometimes the membrane can get damaged. So yeah, just have to put in a new O-ring membrane. There's a little ring that screws into the bottom, holds it in place. Fill it up again with the solution, check the anode and cathode, make sure they're good, and that's it, and then calibrate it. So what you need to know about the galvanic, it acts like a battery based on the electrochemical reaction. So there's a reduction happening inside based on the amount of oxygen and the solution. Like I said, started in 1964, produces its own voltage, and fairly dependable. Much, much better than the polarographic. Much better. So please, golden lead. Yeah, that's what I said. Okay, anyways, yeah, much better than polarographic. So please read these. I'm not going to read them online. There's no sense. I haven't seen any hands go up, so I'm assuming this is a good speed. I can't remember how many lengths there are. Note that the actual output from the sensor is in millivolts, so you'd have to protect from electromagnetic radiation, that sort of stuff. But yeah, they're okay. Polarographic cell. Now, like I said, this was developed over 100 years ago. And the disadvantage, one of the main disadvantages to this is you have to supply voltage for it to measure the dissolved oxygen. Plus, it is not that stable. It's temperature dependent. It takes time to warm up this instrument. It needs calibration quite often. The nice thing about it is, and one thing I forgot to mention with the galvanic probe, is it does not, unless you have voltage applied, it does not use up the anode and the cathode, as opposed to the galvanic probe, because it's like a battery. It's constantly eating away the anode and cathode. Yeah, I'll let you guys read this. It is also filled up with a caustic solution. So you have to take care if you are changing this. Chances are nobody will see one of these ever, but whatever. Okay, galvanic versus polarographic. Galvanic probes are more stable, more accurate. You know, at the lower levels of DO, they, you know, typically about a month to check it and make sure that it's, you know, that everything is good, the solution, the cathode, anode, membranes. Same with calibration, you know, probably a month. So yeah, less maintenance and in the long run cheaper. Whereas the polar graphics, you know, once a week you have to check them and calibrate them. Actually, every use you really have to calibrate them. It's just not a good system. So know this. Know everything on this slide, basically. And be know where to find it if you happen to see it on a quiz coming up. Okay, I'm going to continue. A few seconds. All right, LDOs, luminescent dissolved oxygen probes. So, oh, actually, I will mention, I'm going to go back a slide. Another thing about the polarographic and galvanic probes is they actually consume oxygen in the water, or in whatever your solution you're measuring the DO in. And that, you know, for obviously for a wastewater treatment plant, you know, a 50 megaliter tank, the small amount of oxygen that's used for these probes is you know, negligible. However, for some applications, it can impact the amount of oxygen in that system. The nice thing about LDOs is they just work, and they work well. So I'll get into the how they work in momentarily, but basically they do not consume oxygen. Calibration is very simple. It's now basically done with an air calibration. So you're using the air as a standard. You do not have to worry about things like elevation, temperature, all that. That's all taken care of in the controller with modern LDOs. It does not use oxygen. Downside, of course, is you have to pay for it. It's far more expensive. Calibration, I think I mentioned already. Maybe calibrate it once a year if you feel like it, and that's direct from the manufacturer. You know, that if you feel like it. We're all professionals, so we will calibrate as per the SOPs regularly. But yeah, so they're the cat's meow. They're the best of the best. So I'm going to talk about how it works. Basically, it uses fluorescence to measure the amount of oxygen. And this is, of course, the emission of light by a substance. So as electrons are excited in the orbits, they'll jump to a higher level. And then when they fall back to their normal level, they quite often emit a photon. And yeah, that's what it is. I in the past I would show this really cool video of people walking around showing their teeth, wearing white shirts and all that sort of stuff. But everybody's seen that, so we all know what fluorescence is. So basically, the way the LDO works is it will pulse at regular intervals a violet light, and that will excite the oxygen molecules in the solution that's being tested. And when the electrons fall back to their normal level, then they emit a red pulse. And that is sensed by the intensity and the timing of the red pulse is sensed by the probe. So a blue light is sent out, which excites the molecules, and the molecules will send back a red pulse, which is measured by the probe. So the intensity of this light determines the amount of oxygen in the water or in the solution that you're measuring. Oh, I got a minute. Aaron's going to yell at me soon. Yeah, we'll just go for this last slide. Excuse me. So these LDO probes have no working parts. There is almost nothing to replace, require little calibration, do not consume oxygen, and yeah, there's very little to go wrong with them. All right, Aaron, yell at me. Thanks, awesome. Okay, guys, yeah, just 10 minutes, please, and enjoy. If anybody's got an appropriate YouTube video to share, maybe post a link or something while we're having coffee. Otherwise, I'm going to mute my my mic for 10 minutes. Also, if anybody has any questions, please, now's the time to ask. righty, people. Um, okay, we won't get into how the Imperials are much better than the Stormcloaks, or how the Stormcloaks are just ripping apart Skyrim and are an evil, nasty faction to join, and you'd be basically inhumane to do that because neither. I like that. Okay, anyways, it is time to get back to our people. So we do have two more lectures to go through. They are short, but let's finish off this deal right now. All right, so okay, like I mentioned, the LDOs, luminescent dissolved oxygen probes, work. They're very little calibration. The only thing you have to change or maintain with them is the luminescent covering on the probes. It can wear out over time. The recommendation is to replace them at least every 2 years. So, and they are expensive. Probably, so for the ones we have in our lab, the hack probe, the head is removable, and that head probably costs in the range of I can't remember, $150 ish. So over 2 years, that's nothing really. Yeah, really, there's not, except for the initial layout of this probe, of this unit, there's not much. Yes, exactly. Yes, Roland. Roland gets a little grumpy if you mistreat equipment. I get mad. I just don't show it, and usually have Roland sick Roland on people. But yeah, no. Yeah. Thank goodness for Roland. Place would fall apart without him. But we won't talk about Roland. Okay, so as mentioned, LDOs do not consume oxygen, so it does not affect the amount of oxygen in the solution. Also, LDOs work without flow. So I mentioned that the membrane type sensors, the galvanic and the polarographic, also known as the potentiometric sensors, they need flow around them because they use up the oxygen. So there would, if there wasn't flow, there'd be a dead zone around the probe where the oxygen has been used up. So the LDOs, because they do not consume oxygen, do not need flow. You can just stick it into you can do jar tests, for instance, batch tests, or whatever. Optical dissolved oxygens, typically from the manufacturer, calibrated once a year, and like I said, if you feel like it. Of course, you have to follow the standard operating procedures, the SOPs of every plant. And unless you are working in a large facility, most likely you will be the one calibrating these instruments. So we're going to just talk about very briefly the proper way, the proper method to test water in the field. So ideally, this is covered in biology, in chemistry, and Allison and Dave. So it's usually not part of instrumentation, but with this one, it is of particular importance. So number one, of course, calibration. That is the key requirement to any process control. to be able to accurately read any kind of process, whatever it is. In this case, obviously dissolved oxygen. Then get proper sample bottles. So if it's a laboratory that you're bringing it into, get the sample bottles that they supply. That is of utmost importance. Now, of course, once you're out in the field, people kind of forget the proper way to do things. They'll use their shirt to clean vials instead of the proper velvet cloth, or we'll just grab any sample bottle. But for critical applications, you have to use the supplied sample bottles. Before you immerse the probes and rinse them off. So make sure that there is no deleterious materials that can interfere with the readings. So no bad stuff stuck to it. Place the probe inside the sample that you've collected. Record the results, obviously. And yes, you must put not only your name, date, location, but include partner's name or somebody you're with. The depth. How far out did you measure? Was it 15 meters into the lake at a depth of whatever? What thermoclines were you measuring? All that sort of stuff. And then, of course, clean the dissolved probes with distilled water again, properly store, and yeah, that's it. There's my sources, people. Please feel free to check them. And I think we should watch a video, because right now I'm getting bored. So please bear with me for 1 second. I had it preloaded, but I don't. Oh, no, it's not there. Okay, so please give me 1 minute. Now, this is a 4-minute video, and it just goes through explaining how to change the sensor head for an LDO, and how to tell the controller what type of LDO system you have.
The LDO cap is an integral part of the operation of the LDO probe. It houses the lumiphore material, which enables the probe to measure dissolved oxygen. If this lumiphore is damaged, or the cap reaches the end of its 2-year life, it needs changing. In order to change the cap, take the probe out of its application and remove the old cap and its sealing ring.
So I might note that, or as you're watching this, I'm just going to rewind a few seconds. You will see little flashes of red and violet light from the probe. The violet light is, of course, to excite the oxygen molecules, and the red light is just used for timing. So the oxygen molecules will return a red pulse back to the probe as a result of the violet pulse. And this red pulse given off is to help with the timing. So if you don't see these pulses, your probe is probably not working.
Out of its application and remove the old cap and its sealing ring. When you order a new cap, you'll receive both the cap and the new sealing ring. The sealing ring sits in the sealing groove, and therefore you must ensure that the sealing groove is cleaned and free of debris to ensure a good fit. Place the sealing ring in its groove, finally fit and hand tighten the sensor cap. On your new sensor cap, you'll find a sensor code. You will need to enter this code into your SC controller. This enables the factory calibration of your cap to be uploaded into the controller and your LDO probe to operate correctly. You enter the code via the menu in your SC controller. You enter the code via the menu in your SC controller like this. Select the menu button and then select Sensor Setup. At this point, if you have more than one sensor connected, you would have needed to select the correct sensor. Now select Configuration and then carry down through the menu until you find Sensor Code. You use the up and down arrows to change the character and the left and right arrows to select which character you wish to change. Once you've edited all the characters, press the Enter key. Your probe is now ready for operation.
And I think that's good enough. Alrighty. If there are no questions, if I do not see any hands go up, we're going to go on to chlorination. Good. So please turn to chlorination. Does somebody have a page number for everybody? Thanks, Ryder. Awesome. All right, so you can see my notes here. I think everybody realizes the need for residual chlorine testing of the amount of chlorine in water in leftover in pipes. Do not do the, please do not do the, oh, there's no residual water. Well, let's just run it for, let's just run this tap for half an hour and then test it. That's kind of cheating. But yeah, and my understanding is you guys have already, from asking individuals in the class, you guys already have taken chlorine. So this is going to be a very, very quick lecture. Now, I'm going to, if I'm going too fast to fill in the blanks, start raising your hand or unmute your mic and just say, Frank, can you slow down, please? Because I'm assuming that most people know this already. I still have to cover it. But yeah, I'm assuming you guys know this. So obviously we have to discuss the chemistry behind chlorination. We are not going to go into great detail. In fact, this is going to be a high level, and that's basically all we need from an instrumentation point of view. So there are, and we all know that there are three main forms of chlorine. There's the free chlorine, combined chlorine, and then combination of both these make total chlorine. So yeah, from the instrumentation point of view, this is all we care about. So this is a really nice graphic that It is online. Check the source in the back. So the initial chlorine is added to the water. If there are any organics in that water, the chlorine will combine with the organics. Whatever is not combined is still chlorine, free chlorine, Cl2. Otherwise, the combination of the combined, combined chlorine is still able to disinfect, but not as well. That's right. So free chlorine, combined chlorine, and total chlorine. Good enough. So as soon as chlorine is added, and you guys know this already, it will react with any impurities in the water. It does not react with water itself, but it will react with any impurities. So reacts first with the inorganic, then the organic materials inside the water. And that's the chlorine demand of the water. Again, you would have learned this from Dave. So things like clay, silt, iron, bacteria consume chlorine. If you are using completely pure water, then the chlorine will not react with it. You will not smell the chlorine. It's hard to detect. So that is called free chlorine. If there are organics or inorganics in the water, the chlorine will react with them and create combined chlorine. So chlorination consists of two types of chlorine, really, the combined chlorine and the free chlorine. Combined chlorine is the amount of chlorine that has reacted with the inorganics and organics. And quite often in water systems with pure water, they will actually add organics into the water just to have some combined chlorine. So yeah. So combined chlorine. What causes the chlorine taste and odor? And I don't know, most people should know Michael Phelps. Probably has more gold medals than I have hairs on my head. Admitted to peeing in the pool. So I want everybody to read this for the next quiz. You're actually going to be asked to read two things for the next quiz. Good question, Aaron. Not sure. Okay, anyways, so this is, excuse me. This is the article here. What gives pools that chloriney smells? And everybody knows the spoiler alert. In fact, it's right there. It's all those great little kids peeing in the pool. And it's not just that. I discovered, and here's a pro tip for you. If you decide to bring your baby into the hot tub, please make sure that their diaper works in water. I unfortunately shut down a hot tub by bringing my baby in the pool, and diaper leaked, and that was it. Everybody out, shut down. And yeah, people were not too happy with me. I mean, it's not my fault, I thought, but whatever. Okay, anyways, I want everybody to please read this article. It's very short. It talks about, on a high level, the chloramines, all that sort of stuff, and gives a little bit of history. about it. Pop to the previous slide, yes. Oh, moving on. Okay, I'm going to continue going. Hopefully that's enough time. So free chlorine basically is chlorine that has not combined with any inorganics or organics in the water. Go back a bit. You guys already know the how it dissociates in water. I'm not going to get into that. It's not needed for this course. But the nice thing about free chlorine is potentially it has 100 times ish the disinfection power of other forms of chlorine. Total chlorine is a combination, of course, the free chlorine and combined chlorine. So the way they're ranked is, the free chlorines, 100 times better than the inorganic chloramines. So the chloramines still will disinfect, but not as well. The nice thing about them and why they are sometimes added into pure water systems is they're more stable and they last longer. So we have to talk, of course, about residual amounts in pipes. And I'm going to just very quickly switch over to this page. Now, this is at saferwater.org. And these are the chlorine residuals for each province. Now, you'll notice that BC does not have standards. That's not exactly true. Based on each health authority, they issue out standards, and it's usually dependent on whatever permit, but it's standardized as 0.2 milligrams per liter. So, but this is well worth the read. I highly recommend it. It's a long read. This will tell you basically what you need to know about chlorination when you get out in the field. So please read it now if you have time. Definitely read it when you're out in the field. You need to know this, especially if you are in the wastewater field. Good enough. All right. In the labs, in the chlorination lab, I've mentioned tonners before. These, incidentally, are tonners. So they're 1-ton tanks full of liquid chlorine. How does chlorine get inside our water system? Tonners are by far the most used method. So by actually injecting liquid chlorine into the water system. Another way is, and I'm just fast forwarding. Darn. Okay, another way is by generated on site using a hypochlorite solution. I do not have the slide I was looking for. So the downside with tunners, of course, is chlorine is a dangerous gas. If there is a leak, it is potentially dangerous. We do not like chlorine tanks in residential areas, and that's usually where wastewater treatment plants are. But it's cheap, relatively very inexpensive, especially considering generating on-site chlorine, because you have to buy the salts and all this sort of stuff. It's very effective, very easy to use. Normally, you guys will be offered a chlorination course. I don't know if it's going to happen this semester, but in subsequent semesters, I do recommend taking the chlorination course, especially if you're getting into the water field. All right, I'm going to skip this more chlorine chemistry. And I do apologize. I don't have my, I don't know if there are any blanks on this slide. So unless I see a hand go up, I'm just going to continue. Same with this one. Okay, thanks, Ryder. I'll let you guys read this. And you should just know this. Now, don't worry, Quinn. You're still my favorite. Of course, everybody is who logged on today. But you know, you're still my favorite. Just maybe not as much as Ryder at that moment. So you've probably never heard this from Dave, that he has said that pH is important. I don't know why. I mean, obviously, it could not possibly matter as much of a transducer breaking down or something. But anyways, this is just a distribution of HLCl versus pH. Obviously, the higher the pH, less free chlorine. And same with this here and this. I'm not going to get into the chemistry, but ideally we want to be, you know, around the 7-ish. Well, I'll leave that up to Dave. I didn't say anything. I'll let you read this too. And this one, I'm not going to go over it. Okay, cool. So, does anybody want to share where chlorine was first used in North America? Anybody? Hopefully somebody knows this, wants to put up a hand, unmute their mic and talk for 30 seconds. Darn, no takers. Okay, fine. You're going to just have to listen to me. So my understanding is it was first used in England. There was a man named John Snow who came up with this really weird theory that there was yes, we're talking about England. Had this really weird theory that you could catch illnesses from water and not, you know, from the miasma, the air that which everybody knew caused illness, you know. And so so they started chlorinating water systems in England at that time, or shortly after. Yeah, exactly. You know nothing, Jon Snow. So nobody has any excuse whatsoever to not know his name. Is this the Broad Street Pump video? I do recommend watching the Broad Street Pump video. It's fantastic. It's one of my favorites. I can't preview this one. I'm sorry, Aaron. I trust you, but anyways, so watch it. It's entertaining. It was first used in North America in with cattle. They found that cattle that was given chlorinated water lived longer, became fatter, plumper, and somebody said, hey, if this works for cows, why don't we try it on humans? So I don't know why they didn't, and maybe they knew about, some of the chlorination attempts earlier in England, but that's basically where it came from. So how well is chlorination? You guys all know this. Viruses, I believe the contact time is 20 minutes. I'm sorry. For Giardia and cryptosporidium. So viruses, it's almost instantaneous. So it kills it. Virus is dead, which is nice. Bacteria, same thing. But things like cryptosporidium or Giardia, you need longer contact time. And that's why Health Canada, as well as Interior Health, requires 2 forms of disinfection. So, which is usually chlorination and UV. I've got some cool videos here. We're not going to watch them. Sorry. But yeah, feel free. But we are going to talk about the measurement methods. I do want to try to do conductivity. It's a very short lecture. So measurement methods. We are going to be talking about colorimeters, which everybody knows about. Polarographic, which we learned about in the previous lecture. Galvanic, which we learned about in the previous lecture. These 2 you get to do in chem, so we're not going to talk about that. And same with this one. Okay. I don't think I need to discuss how to use a colorimeter. I'm pretty sure everybody knows how. If you don't know, please just email me. Don't raise your hand now or whatever. Yeah. Anyways, basically, once the pill pack is added to the solution and the color changes based on the amount of chlorine, the wavelength of the light is measured, and that gives a fairly accurate indication of how much chlorine is in the sample. Cool. Advantages, well, I mean, it's cheap, easy to use, all that sort of stuff. Problems, you have to use reagents. The pill packs, they do have a lifespan, and yeah, must use pumps, valves. It's I mean, you've got to constantly sample, batch sample, all that sort of stuff, and cannot adjust for pH or temperature. So read the open electrode buffered system. I will not test you on it, but know it. Please, I'm going to fast forward for a second. Please read this. I'm not going to go over it, but you should know it. Please read this. Again, I'm not going to go over it, but you should know it when you get out there. But the polarographic membrane sensor is it uses the same principle as from the previous lecture for DO. So the polarographic is not as user-friendly as the galvanic sensors. They do require a voltage, do require more maintenance, do require more calibration. So basically the same problems as the galvanic. The galvanic, where were we? Oh, right here. Again, the same operating principle as that I mentioned before. So luckily you don't have to rememorize how to do it. Please read these slides. I'm not going to go through them. Again, over time, you do have to replace the solution inside both units, polar graphic, solid galvanic. The anodes and especially the anodes do wear off. The membranes can wear off. Usually, with these sensors, it's just a pre-tension sort of fit. You slide it up. You still have an O-ring on there, but you may have to unscrew and screw in the membrane, just like with the DO sensors. Good enough. Here is pictures of different stuff, and yeah, no assignment, so I'm going to skip over that. Please check my sources though. And good enough. Any questions with this? That's what I like to hear. None. All right, we have now 10 minutes to finish off conductivity, and I think we can do it. All right, conductivity, TDS, TSS, and measurements. Darn, I set this one up earlier. Unfortunately, I had to close down my my windows. Last night was not fun. I actually had the black screen of death for Windows 10 because one of you guys gave me a virus, and I've been fighting with this stupid computer since then. Let's watch a video right now. Good. Okay. Sorry, guys. Frank doesn't know what he's doing. Give me 1 second. Good. So you can see that there is no conductivity in pure water. Tap water, of course, does have some dissolved solids, so a bit more conductivity. Far more dissolved solids in river water, groundwater, etc. So higher conductivity. And those of you who have done the last portion, I just had you throw pinches of salt inside the water, see if there is indeed a trend. And you can see that the conductivity does increase with the addition of impurities, salts in water. Okay. So, and I'll talk about the quiz coming up towards the end of the class, or towards the end of the lecture. All right. Conductivity, that is the degree to which something will conduct electricity. It is the opposite of resistance. In fact, in the olden days, the symbol for conductivity was the upside down ohm symbol, which is the symbol for resistance, and it was the backwards mho. However, the SI unit for conductivity is the Siemens. So we don't use moles anymore. However, you may run into it. So pure water is a very, very poor conductor of water. If you guys remember, in class I showed the dissociation of water, how it dissociates, but it's the water molecule is actually a very stable molecule. So conductivity, as I mentioned, is measured in Siemens, and conductance is 1 over resistance. So it's nice and simple. Resistance is the opposition of flow of electrons, and therefore conductance, which is the reciprocal of resistance, becomes the measurement of the substance's ability to allow electrons to flow. Since water is a very poor conductor of electricity, it is a quick and dirty tool to measure how impure the water is. That's all. It doesn't say what's in the water or all that. It's just, like I said, quick and easy and cheap method to see how impure the water is. So it's non-specific. It can't tell you what's in the water, but it can tell you, give you an idea of how many impurities, dissolved solids inside the water. Where is it used? Basically everywhere. So, but mostly things like boilers, cooling towers, breweries, very important. That sort of stuff. Normally, at this point in the lecture, I would take everybody on a field trip. So unfortunately, you're missing a field trip to show you a cooling tower. And what a cooling tower is, it's when you guys next semester return to Okanagan College and look outside C-140, you'll see a great big silver thing behind a fence, very tall. And that's a cooling tower. And what a cooling tower is, basically a radiator that you would pump a liquid through and allow air to flow through, allowing it to cool. And so it's used in many buildings and industries. So you have to, for all these, you have to make sure that the water is pure. And so this, so conductivity is, like I said, a cheap, easy way to test the purity of water. You can see these, the conductivity approximately. Obviously, you don't need to know this. Just know that pure water is not conductive. All right. This shows basically how it works. You have 2 probes inside a solution. One is sending out electrons, so the negative side is sending out electrons toward the positive side. If the solution does not conduct electrons, you will not have current flow. That simple. Quite often it's an AC source. It can be a DC source. It is dependent on temperature as well. So the higher the temperature, whatever. You can see that. Comes in numerous flavors. Quite often in the water industry, you will just see something like this rather than something like this, individual probes inside the water. So this happens to be a 2-cell probe. 2-cell probes just have 1, 2 probes inside there. And they're good for low-end measurements, that sort of stuff. So very accurate where they're testing. You can add the longer lead lengths if necessary. Yeah, generally don't need as much calibration. So no oldies. Read this. Be able to find them. Find it if I ask on a quiz coming up. Oh darn! I only have 3 more minutes. I got to hurry up. There's also 4 electrode conductivity. So you actually have 4 individual probes. Advantages, disadvantages, not as good on the lower end. But more stable with your measurements. So if you have changing conductivity, yeah. Again, know where these advantages and disadvantages are. There's also another type of conductivity probe. This one is electrodeless. So I'm going to let you read this. I hope there's no blanks. If there are, please put up your hand. But everybody should recognize this kind of drawing. Now, it's very similar to a meg meter. You have 2 coils inside here that generate a magnetic field. And as a conductive fluid is passed through, a current is induced inside that conductor. Anytime a conductor passes an electromagnetic field, a current is induced inside that conductor, which happens to be water. So exactly the same principle as a meg meter. However, they look more like this. And actually, I'll just go, this is what they look like. So as water passes through electromagnetic field is generated in one coil and then measured in another. And based on the amount of salts inside that water, there'll be a higher current, more voltage sensed in the second coil. So yeah, nice, simple. Problems with this is they're not that accurate, but they just don't wear out. Yeah, they work. But like I said, in water, you don't.
Player.
Yeah. I've seen them in water treatment, but usually, you want higher accuracy. So you would usually use the probe methods. They're pricey too, very expensive, and you also need flow. Whereas the probes, you do not need liquid flow. Good enough. So this gives just shows the range that they can measure. So for water, pure water, you want the 2 electrode. That looks like time. Unfortunately, we'll have to leave it here. Total suspended solids. Thank you very much, everybody, for showing up. I do apologize. I'm now going to talk about the quiz coming up. So I'm going to take more of your time. And yeah, I do apologize. So the quiz. I am going to post on Moodle a quiz. Try to do it, please. Well, number one, obviously by yourself. We don't want everybody, holding hands and being with each other. It is going to be on Moodle. It will be timed. You will only have 1 shot at it. It's probably going to be randomized questions, so just out of a question bank. So similar to Owen's quizzes, and later on, I use them in second year. I tried to avoid them with first year, but it's kind of hard now. So please just watch Moodle. I'll put out a notice when the quiz is up. I still haven't made it because of my black screen of death last night. And start studying for a great big comprehensive 2-hour quiz, which will happen in about 2 weeks. Cool. And if that's it, I guess I'll see you guys. Oh, what material will the quiz cover? Well, you know what? That's a good question. And I'm glad you asked it because I had no idea. I hadn't thought about it till now. So everything right up to this point is covered. How's that? That's fair. It's an open book. So everything that basically since the midterm up to this point. All right. Now somebody asked for page 210, slide 11. If you can give me which one it is, like conductivity, all that, and then the slide number, I'll turn to it. So, Michael. Oh, yeah, I know. That's why Taylor's my favorite. Anyways, okay, good enough. I'm gonna be on. Yes. Right now, yes, Megan, and I do apologize. Right now, things have been a little bit hairy, so I will be spending, well, basically the remainder of my life over the next month trying to catch up on marks and all that sort of stuff. So, please give me feedback too. Email me if you have any suggestions and all that, and yeah, I'll see you guys during the lab. Oh, and please log on for labs. We will be lecturing, but I'll also be probably covering some labs. Also, everybody get your labs in now, like as soon as you can. I recommend that you do not drop them off in my office, please. Scan them and email them to the wet course email, or take pictures of them and send them to me. But do that right away so I've got a bank of marks in case, we get sick, I get sick, or whatever. We can. I don't care. So the question is, can we combine the labs into one section for Friday? Yep. I still have to. I'm still going to be with both. I have to because some people work and all that. But yeah, you guys can come to whichever one you want. I don't recommend coming to both because it's going to be boring. And hey, if everybody comes to the first one, nobody has to come to the second session. There won't be a main one. Formals, yes, you have to do them. Yes. I'll let you know more on labs later. The deans are talking about it and all this sort of stuff. I mean, right now, COVID-19 is this has never happened to the world. Not in the last 100 years. Well, actually, even 50 years. And that's why we really don't know what to do. We're following the advice of public health officials. My mom, she's in her 80s. She remembers not being able to go to school or swim in pools and stuff because of polio outbreaks, or polio and smallpox, and we're just not used to it now. So yeah, so everything's kind of up in the air. But don't worry. You guys, Wet 123 is good. You'll be taken care of. All right. By the way, you guys now can unmute your mics if you want to. It'll be hard to listen to, 17 people talking at once, but.
I'm just going to test it. Can you hear me?
Oh, yeah. Hey, that's perfect.
Nice. Cool. Thanks, Frank.
Yeah. Hey, I am actually going to click on Aaron's, or excuse me, Aaron's video right now. Trusting him.
The noxious vapors that cause disease.
Yes. Well done. I love this video. I highly recommend watching it. It's entertaining the way